Okay, so welcome back. Today we're going to take a look at some aspects of the electric power system that feeds your home or office and feeds electricity to just about everybody on the planet. And in this video, we're going to talk a little bit about the electric power system frequency. And if you know anything about frequency, you might think, well, what's there to know? You've got this sine wave, which represents the voltage at your wall outlet supplied to you by your power company. And it goes, in the US, it goes like 120 volts RMS, which means it goes up to a peak of about 170 volts and down to minus 170 volts. And frequency is just a measurement of how often that happens every second. And here in the US, it's 60 times per second, or 60 hertz. Other parts of the world, it's 50 hertz. So you might say, well, yeah, 60 hertz, what's there to know? Frequency, piece of cake. Well, no. It turns out that when you're talking about electric power systems, frequency is an extremely important, and most people aren't really aware of it, but it's kind of the heartbeat of the power system, and it's really fascinating. Now, we've talked before about power systems. We did some videos talking about how to simulate dynamically with a C# software application, how to simulate a big turbine generator like you see here. And this is a big monstrous generator, and you can see here a little cabinet where a person walks up to and opens the cabinet, so you get a little idea of how big this is, because this is about be 6 or 7 feet tall. So this is a big monster generator, and we talked about how you can simulate that. You've got, in this case, you've got steam coming in these big pipes, and they're spinning a turbine, and on the same shaft you've got this electrical generator, which basically takes a DC field and rotates it through some AC windings, and that generates a sine wave like this. And in this case, it generates 3 simultaneously to give you 3-phase of alternating current voltage. So we talked about how to simulate that with a C# application. We also talked about with all of the generators and loads connected together, how do you figure out where the power flows? So we talked about doing load flows. We also developed an application like you see here, and this is measuring the actual frequency of the wall outlet voltage at my location. And it's a very simple C# application, and the only hardware it's using is a very low-priced, inexpensive Arduino hooked up to the USB port on my computer, and it's measuring over time the actual wall outlet frequency. And you can see it's centered here around 60 hertz, and I'm showing about 60 minutes, or the last hour, of frequency measurements of my wall outlet voltage. And we'll see in a little bit how this is controlled by your power company, very narrow range. But we're going to take a look at what this all means. 60 hertz, so what? What does that all mean? Imagine you're driving your car down the highway, and you've got your foot on the gas, and you're going at 60 miles an hour. Then let's say you're approaching a mountain, and suddenly your car has to go uphill, which means it's facing a more difficult challenge. It's going uphill is more difficult than going on a flat piece of highway. So what's going to happen to your car if you have your gas on the pedal and you don't change the position of the pedal? When you go up that hill, your car is going to do what? Well, it's going to slow down, because there's a lot more load on the car, but the gas, the intake, the energy hasn't increased because you've left your foot at the same place on the gas pedal. So what you have to do is you have to press down harder on the gas pedal to put more gas into the engine to give it more energy, so it will speed up and maintain that 60 hertz. Conversely, if you are at the top of the hill and you start going down, you leave your foot on the pedal, your car is going to do what? Well, it's going to speed up, because it doesn't need the same energy going downhill to maintain 60 miles an hour. So what you're going to have to do is put on the brake or let off the gas. So if you're going uphill, you're getting overloaded and you have to add more gas. And as we know, it takes time to add gas and for the car to respond. And as you're going downhill, you need to let off the gas to maintain 60 hertz, because it's going to start going faster. This is exactly the same as with these big generators, okay? When the generator is spinning, it's got a certain amount of steam coming in, like your foot on the gas pedal, and it's turning this at a certain speed. If you get more customers turning on their loads, this thing is going to have to put more gas in or put more steam into the turbine to turn this generator at the same speed so that you will be able to serve those customers. So it's exactly the same as driving your car. If you get too much load, what's going to happen? Well, it's like going up a very steep hill. Maybe your car can't handle it. And what's it going to do? Well, you're going to have the foot as far as you can down on the gas pedal, but the car is going to stall and maybe go backwards if it's a really steep hill. Same thing's going to happen in the power system, right? So it's very important that you make sure you have enough generation and that you maintain the right speed, because speed is a very good indicator of how overloaded or underloaded your system is, all right? Just like measuring the speed on your speedometer of your car, if you're supposed to be at 60 and you're at 30, you know that you're overloaded. You can look at that meter, you can look at the speedometer and say, hey, wait a minute, I want to be at 60, but I can only get to 30. You know you got a big problem. Same thing on the power system. So that's why this measurement of frequency is such an excellent indicator of the status of the power system. And in my case, I'm in the eastern US, and the indication of frequency in the eastern US tells me, is this overloaded? Is it underloaded? Is there a problem in the eastern US? And if it's, if this gets down to a very low frequency, there could be big problems. You can't supply the load, and suddenly these generators are going to stall and trip off, and suddenly you're going to have these big blackouts. So it's really interesting to look at not only your frequency, but the frequency of other places in the world. Now, because this is so important, here in the US and other places in the world, they are very strictly regulated into what the frequency should be under normal conditions. The US government regulates power companies to make sure that they maintain their frequency in very strict range under normal conditions. Now, in very difficult conditions, it can go outside that, but the goal is to try to monitor the system and make sure that it stays in that range. And the way they do that is they monitor the frequency, and if the frequency is getting too low, you send a signal to this generator that says, hey, add more steam to this turbine, get this thing running better because it's slowing down and we're running out of energy, you need to speed up. And conversely, if it's going too fast, hey, slow down. So there's some very complicated control systems involved in all of these generators that make sure that you are operating in a very tight range of frequency. Now, if you look here, here's the frequency in the eastern US for the last hour, and you can see it's always in this red range. And what I've done is I've set this up to show plus or minus 0.05 hertz from 60. And you can watch this over days and weeks and months, and generally it will never stray out of this range. And that's because there are such strict regulations to make sure that the generators are controlled to be within this range of frequency. So you can imagine here in the eastern US or other parts of the US, there are these big, huge control systems with all of the generators. There's probably thousands of generators in this area, and they all are being told second by second, hey, speed up or slow down because we need to maintain our range right in the very narrow range that's required. So what are those requirements? Well, here is a map from what's called the National Electric Reliability Council here in the US, or NERC. And they're the ones that are assigned the responsibility to make sure that we have reliable electricity. And you can see that they've shown that the different, what they call interconnections, are separated into 1, 2, 3, 4. The Western interconnection, as we showed, Western US, the ERCOT, which is Texas, the Eastern connection, which is what we showed before, and then the Quebec interconnection. And as an example, they have requirements that say, like is shown in this graph. And what this says is you need to maintain your frequency within, here you can see 60 hertz right down the middle. Here's 61, 62, so this is over frequency, and below that is under frequency. And what they're saying is, on the x-axis, you've got time, right? Some 0.1 seconds to 1 second to 10 seconds to 100 seconds. And this graph is saying your frequency can go outside of this narrow range, but only for a short amount of time. So for example, this shows that I can get, my frequency can be down to below 59, but only for about 10, 20, 30, 40 seconds. Then we have to do something. And what they do is they will disconnect some load, some customers, automatically, because it says, hey, we've got too much load, not enough generation, so we have to cut off some load so that we'll get back to the right frequency. So for example, it can't go down to 58 for more than, like here we have 2 seconds. All right. So but after about 2 seconds, if it's at 58 or below, you've got to disconnect some load. And the same thing with an over frequency. So this says, you're generally going to be between 60 and 59 and a half. And then when you get down below that, if you get down to like 59.2 or something, you've got maybe 60, 70, 80, 100 seconds before you have to do something. But keep in mind, this is a dynamic system. Your generators, all you have to do is feed some more steam into the generator and it will speed up. So you send out the control signals and speed it up. But just keep in mind, these are big, massive machines. So it might take, 30 seconds between the time you get the signal that says, hey, speed up, and the time that the steam actually gets in here from the boiler and into the turbine and actually speeds the thing up. So it's all a very dynamic and very interesting situation, but you can see it's a very narrow range that you have to maintain, generally between 59.5 and 60.5, as we see in here. And you can look at this over weeks, days, months, for a long period, and you'll rarely, if ever, see it venture outside this plus or minus 0.05. So very interesting. Now, other parts of the world, you may see some much larger variations. We can scroll out here and see if anybody goes outside. I've noticed that often United Kingdom can go quite a bit outside that range. Other countries can go outside, but generally in the US, it's going to be right within that range. This is a map that gives you a instantaneous look at the frequency of the electric power systems of many countries around the world right at this very moment. All right. So all of these colors represent the relative frequency of the electric power systems in those countries within, the last 5 seconds or 10 seconds or whatever. So you can see that there's a variation in different countries have different frequencies relative to what's normal. So it can tell you can look at this and say, hey, this part of the world is the frequency in India here is kind of low right now. And in Brazil, it's a little bit higher than normal. So it's really fascinating. You can use this to kind of get a heartbeat or a pulse of the electric power systems around the world. So the first thing you want to do is go to this website. It's a free website, and it's run by, you can see on the left, the University of Tennessee at Knoxville here in the US. And it's the Power Information Technology Laboratory, and it's at PowerIT, POWERIT.UTK, which is University of Tennessee at Knoxville.edu. And you'll come to this main page, and apparently they are working in conjunction with the Oak Ridge National Laboratory here in the US. And you can click on this FNet, which is Frequency Net Grid Eye. And that describes how they have set up this network around the world, and they are reading the frequencies of the different power systems, And I believe it's all volunteer people. And what they do is they send out this little device here and to volunteers, and they connect it over the internet, and they are able to take the real-time data from these devices and project them onto a Google Earth map and show you the real-time electric power frequencies. So really fascinating. If you look down here on the bottom, it shows what each of these colors means. And basically, if it's green anywhere, that means that it is in a very narrow range around normal frequency, right? And that range is plus or minus 0.01 hertz. So you can see it's a very narrow range, 1/100th of a hertz. And in the US, it would be around 60 hertz. Other parts of the world, it might be 50 hertz. So green, anywhere you see green, like here in the Western US, that means it's plus or minus 0.01 around 60 hertz. As you get into the yellow, orange, red, and brown, that means the frequency is relatively high. So if it's yellow, it's high by 0.01 to 0.03 hertz. So in the US, it would be 60.01 to 60.03. And as it gets darker orange red, it goes to 0.03, 0.05, and then 0.05 to 0.07 is brown, and then dark brown is 0.07 to 0.09, and then darker than that, it's more than 0.09 hertz high, okay? Conversely, when you get into the light blue and dark blues, that means it is low. So you can see here in the United States, the eastern and western parts of the US and Texas are all about minus 0.01 to 0.03 hertz below 60. And you can see the western US just came back to within 0.01 hertz. And the eastern US is still 0.01 to 0.03 low. So you can see at a glance where everybody is. Australia is a little bit high, China's a little bit low, Brazil is a little bit high, Mexico and Texas are a little bit high, United Kingdom is a little bit high, and so on. So really fascinating. And what you can also do is, if you have done this frequency monitor, you can compare the results of this map to what you read in your own outlet. Right now I'm seeing 59.97, which should tell us, yeah, it should be kind of a light blue because it's below 60. And so it should be like minus 0.01 to 0.03 because it's 0.97. And as expected, I'm here in the eastern half of the US, and it matches what I see here. It's down 0.02, 0.03, and it's light blue, which makes sense. And if it gets back to around 60, it will go back to green. So really interesting. So what you could do, wherever you are in the world, you could build this simple C# application and get an Arduino and compare your results like we're doing here to what is measured on the on this map. And you can see it went back to green, and here we are, 59.99. It makes sense because green is plus or minus 0.01. So really interesting, and it also tells you that these are updated fairly quickly to match what we see here. Now, one thing I want to talk about is, you see these big blocks of color. Why do they have blocks of color? Why is, for example, the US has the eastern US, and it has the western US, and then it has Texas as another block, and then up in the province of Ontario, Canada is another block, and if you go over here you can see Alaska in the US is another block. So what's going on with these different blocks of colors? Well, in the US and in many places around the world, the electric power systems are set up so that whole sections of the United States are all tied together in one big massive grid. So when you plug into your wall outlet in the US, the wires that go from your wall outlet through your house to the wires to the power company on the pole outside your house, those keep going, and they're all connected in a huge grid that ultimately, in the case of the US, if you're on the eastern side of the US, all customers and all generators in this area, even up into Saskatchewan, Manitoba, Ontario, Canada, and all of the eastern states, Florida, New York, Maine, are all tied together in one massive grid. So why do they do the massive grid? Well, one major reason is it's more reliable. So for example, on the western US, you can see in California, there's Los Angeles. That's a very big metropolitan area, lots of load, lots of customers. If they're all tied together in a grid, then they can benefit. For example, up in British Columbia and Washington, there are hydro plants. So what they have is they have high voltage connections running down the coast to Los Angeles from Washington, British Columbia, that serve this hydropower electricity down into Los Angeles. And then there's big power plants out in the desert around Arizona, New Mexico, and those power plants can feed Los Angeles. So, for example, if an area of Montana, for example, suddenly lost some generation and needed some power, since it's tied in this grid, it could say, hey, I need some power over here. Give me some power from Washington, and it's a lot more reliable. You don't have to rely on just your own generation, and if you run out of generation, you have to shut off all the power. So it's more reliable. Now, the downside is, for example, let's say there was a big problem in Los Angeles, got overloaded and nobody else could give it enough power, the entire grid could go down. So, there's good sides and there's bad sides to it, as with anything in the real world. You have benefits and you have disadvantages. Over time, they have decided in the US to break up the grid into an eastern half of the US, including parts of Canada, a western half of the US, and for whatever reason, Texas has their own isolated grid. Now, when I say these grids are isolated, technically they may have interconnections between them. For example, there are some interconnections between eastern and western US, which are DC, direct current, which means they're not synchronous. They're not tied together synchronously, but they can provide some power across them. For all intents and purposes, these are isolated grids, okay? So there's a grid in the eastern, grid in the western, there's Texas, and up in Alaska, there is a separate grid in Alaska. And you can see Canada is tied to parts of the US, and Quebec has its own grid, and then Mexico has its own grid. And if you look around the world, you can see Australia, of course, is an island, it's got its own grid. China, Saudi Arabia, you can see Europe, Germany, Poland, Romania, France are all one big grid. And at this present time, they're all about normal frequency, which is, I think, 50 hertz there. United Kingdom is a separate grid, and you can see it's a tad low. Norway, Sweden, Finland are a little bit high because they're orange, and now they're coming back. So now, as you may have imagined, one of the major components of all of this, controlling generators to maintain frequency, is the field of control systems. And of course, it's all about control systems and building control systems that can control your machines to make sure that they maintain the right range. In the future, I may be doing a series of videos where we develop something like this, a C# application I developed that shows the different types of control systems, proportional, integral, PID, controllers. And you can see I can set it to, in this case, 60 hertz, and I can change it. And you can see the control system in real time responds. You can get a good feel for how control systems work, and you can change what type of control system and that kind of thing. So anyway, if you like any of these videos, please hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.